Hey, what is a mega number and which one is my favorite? These are the questions posed by Singing Banana, otherwise known as Dr. James Grime, one of the YouTubers who actually helped inspire me to make this channel here by being one of the professors interviewed very often in Numberphile. So thank you. But more salient to this video, he has made a playlist where he has invited many mathematics YouTubers to simply talk about their favorite number over 1 million, or a mega number. So in this video, I'm going to talk about mine. I will have a link for that playlist in the description below in case you're watching this outside of that playlist. These are my favorite mega numbers. You'll notice that I said mega numbers, right? There's two in this case. Asking me what my favorite mega number is kind of like asking me what my favorite movie is. I've got a few. Favorite superhero movie, favorite action movie, favorite rom-com, whatever. Likewise, I have two favorite mega numbers. One that inspired me when I was a kid, and one that I have found inspires other people. As a teacher, inspiration is kind of one of my big metrics here, because I love seeing when a student's like, whoa, that's crazy! I can take that process and I can make something new with it. For me, that's how I sort of rank these numbers. The number I want to talk about first is the one that inspired me as a kid, a Googleplex. It's not that obscure, it's not hard to understand, but as a kid, it sparked my imagination, and more importantly, it made me look at patterns that I thought I knew in a different light. Here's how it went. My dad comes to me and he says, Derek, there's this number that's so big you could never fathom it. And I said, okay, I can't fathom it. Good job. So when that didn't work, he came back and tried again. He told me how to find the number. It was a Google, 10 with 100 zeros, and this is enormous. He said, there's not enough atoms in the universe to make up a Google. I'm like, all right, that's pretty big. And for a while, that was good enough for me. But he stopped being able to wow me with how big a Google was. Eventually, he had to move on to something else. He said, okay, Derek, there's this other number. It's even bigger than a Google. It's a Googleplex. And I said, okay, what's that? And what he said was, it's 10 to the Googleth power. That's enormous. That's so big that it would take a while to write. I mean, think about it. It's 10 raised to the 1 with 100 zeros. That would take a while to write, wouldn't it? But the thing is that what's really interesting is if you wanted to write a Googleplex itself without the exponent, you would run out of atoms in the universe before you were able to just write down the number of zeros in the number. But here's where I got inspired. It's when I figured out that I only needed 7 characters to write this. I mean, think about it. We write a Google as 10 raised to the 100. So couldn't I just write a Googleplex as 10 to the 10 to the 100? Yeah, I could. And this is what's really fascinating, is that once I saw that pattern, well then we were off to the races. What if I said 10 to the 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 10? What if I did that 100 times? And that right there sparked my imagination. It was huge. It wasn't why I became a mathematician, but that aha moment, that feeling was something that I found that I craved as I went through and did my physics degree and eventually my master's in math. In fact, that's part of why I went into teaching. I wanted other people to have those aha moments. And that brings me to my second number. It's Graham's number. And yes, in certain mathematics circles, especially online, it's a little cliche. The reason I love this number so much isn't necessarily just because it's enormous or was used in a paper, but more accurately, how people react when they learn about Graham's number. If you're already familiar with Graham's number, stick around to the end of the video. I have a little treat for you. And if you're not familiar with Graham's number, then what I want you to do as you listen to the following explanation is really try to see where the patterns are. I want to see what you guys come up with when it comes to making larger numbers or extensions to Graham's number. In fact, I've got a little challenge for you at the end of the video. To understand Graham's number, not necessarily the context from which it comes, although that is an interesting rabbit hole, but rather just the number itself, we really have to understand a particular chain of operations. You probably already know the first few of these operations, and we're going to extend that pattern on from there, a pattern that has been there all this time, but you may never have even realized. The way I'm going to do this is I'm going to start with a zeroth operation, then move on to a first, and a second, and a third, and a fourth, and so on and so forth. The zeroth operation is just counting. It's what happens when you add 1 to something. So if I say count up from 8, you would get 9. Not too hard. The first operation is addition. The reason I'm framing it this way is because inside of addition, you will find repeated counting. That's why we put that as sort of the ground level. Straightforward enough. The second operation in this chain is then multiplication, because inside of multiplication, you'll find repeated addition. So based on this, take a moment and try to figure out what the next operation in this chain is going to be. Go ahead and pause here for a second. Here's the answer. If you said exponentiation, you were correct. because inside of exponentiation, you find repeated multiplication. This is a pattern. If you're starting at exponentiation and you want to make the next operation up, you simply have to do repeated exponentiation, and that becomes the next operation. And in this case, it's called tetration. I did an entire video on tetration, and I've got a link in the description below. But one really important question is, how do we actually notate this so we understand what's going on? Well, the way we're going to do it is we're going to replace the caret in exponentiation with an actual up arrow. What we can do then is simply say that tetration is 2 arrows, and the next operation up will be 3 arrows. It's not necessarily obvious, but something dramatic just happened to the output of this function. You see, addition, multiplication, exponentiation, and tetration all require 2 numbers to work with. They take those 2 numbers and then they do that operation. If you keep those 2 numbers the same and you look at the outputs of doing each operation, then the number goes up very, very, very quickly. For example, if I take 3 and 3 and use those as my 2 input numbers, when you add them, you get 6. When you multiply them, you get 9. When you use 1 as an exponent, you get 27. And when you use 1 in tetration, you get like 7.6 something trillion. That's the dramatic increase that we're talking about. So these numbers have become incredibly large, incredibly fast. Now I want you to pause and think about that for a second, because you may be able to figure out where I'm about to go with this to make this go up even faster. What's the next operation in this sequence? Well, the reason we called this one tetration is because it was operation 4 in this chain. We're going to call the next one pentation, and we get that by simply adding another arrow. This number is preposterous. Let's just look at it really quickly. What this means is do repeated the thing before it. Well, okay, that means repeated tetration. To actually figure out what that means, let's unpack it. We have 3 up, 3 up, 3. That doesn't seem too intimidating, except remember that we said that 3 up, 3 was about 7 trillion. What that means is we replace this one here with about 7.6 trillion, which means we raise 3 to itself 7.6 trillion times. That number is insanely large. That number is so large, we don't really have an easy way to write that one down. It is most definitely larger than a Googleplex. And what's really interesting is it only took 5 little characters to write it. But we're still not quite at the point where we can understand Graham's number, because you see, what we're building up to is the starting point of Graham's number. Here's how we get that starting point. We're going to call this starting point G0. G0 is 3 up, 3. That's right, hexation. We are talking about the operation that comes after pentation. This number right here is stupendously large. Let's unpack it a little bit just to see what it looks like. This right here says 3 hexation 3, which turns into 3 pentation 3 pentation 3, which turns into 3 pentation, that silly, insane large number. That means do 3 tetration 3, that silly large number of times. That is a ludicrously large number. Now, you really should be getting a feeling for how fast these numbers are growing. But more importantly, you're now seeing the pattern that has been lying in plain sight this whole time. So that's G0. G1 depends on G0. The thing that G0 tells us about G1 is how many arrows go here. That's right, that simply tells you how many up arrows you need. There are no longer words to really adequately describe how large this number is at G1. The fun part is that this pattern gets extended because G2 relies on G1 in the same way, and G3 depends on G2 in the same way, and so on and so forth. Graham's number is G64. Now, at a certain point, you just kind of throw up your hands and go, okay, that's fabulous. That number is, good job. That you've made a large number. Okay, the reason that I love this number so much is not so much that it is huge, although it is. It's the feeling that you get every single step of the way of creating something that's even bigger. But more importantly, that feeling you get when you start understanding what you could creatively do to try to generate an even larger number. So here is my challenge to you, dear viewer. What I want you to do is to put in the comments a description of your idea for an even bigger number. What I want you to do is to describe accurately enough what that number is. I have no idea how I'm gonna ever be able to compare the numbers that you guys come up with, but I want you to try to come up with something. That's the reason I like Graham's number so much, is because people then go think and make stuff on their own. So, for those of you who already knew Graham's number, I promised you a little treat at the end of the video, and here it is. This will also serve as my entry to my own little contest. This number right here is the biggest number that I have ever included in any video I have ever made, and I was using it to illustrate the idea that no matter how big the number is, it's still less than infinity. How did I make this number? Well, here is G64. Turns out you can make a number that is breathtakingly larger than G64 by simply saying G65. Remember that however large Graham's number is, G65 simply says 3 with Graham's number up arrows in between, 3. That means that this number here is incredibly sensitive to being increased. So what if I said 66 or 67? Or G64, right? I mean, that says make G64 layers of it. But why stop there? Why not simply say G sub G sub G sub 64? In fact, I see a pattern here. I can invite some recursion into this. I can say G sub dot 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 G64 dot 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 64, right? I mean, that just means write this down G64 times. But here's the interesting part. I'm looking at G64 again. Why don't I just do that entire process again with that 64? And again. And again, and again, and again. So, for practical reasons, I stopped here, and well, this is the number I came up with. So, this formally is my submission to my own contest, and that's gonna wrap this video up. I hope you watch other videos in this playlist, because you're gonna find some very interesting, thought-provoking numbers out there. Thank you to Aragami for helping me do this. Thank you to all of my patrons for all the support you give. I couldn't do this without you. And congratulations to you on reaching the next term in your own Graham's number, Taylor expansion. I'll see you next time. Thanks for watching. If you like this video, please click like and subscribe. If you really like the video, come on over to our Patreon page where you can get involved and see all the cool stuff we're doing.